Could you say that again, please?
Electric fields tend to be something that a topic that tends to be misunderstood quite a bit. So I need you to really recognize something. Even though we're going to be drawing electric fields two-dimensionally on the paper, electric fields are actual three-dimensional. So perhaps you've seen examples of a Van de Graaff generator, and when a person places their hand on it, how the hair stands up on its end. The hair on your head is going to stand up on its ends. Every hair will, and it'll go ahead and radiate in a three-dimensional way. So it's not going to just be like a mohawk. It's going to actually go ahead and spread out completely in all directions. So please recognize that an electric field is three-dimensional. Okay, an electric field surrounds electrically charged particles. So if a particle is charged, it will have an electric field. Obviously, a positive charge or a negative charge. Neutral charges will not have a field. However, neutral charges may be affected by an electric field. An electric field does exert a force. This is very important, and this will help explain that concept of electric force. We can actually move charges around because of an electric field. An electric field is a vector field. Remember, we've talked about vectors in the past. A vector has a magnitude and direction. And in this case, it being a three-dimensional field, there are multiple directions and multiple magnitudes. Remember, magnitude is absolute value. Magnitude is a number. Magnitude is strength. An electric field is always strongest near the source charge, and it becomes weaker as you go further away from the charge. All right. And of course, we have a formula to give you here. The electric field strength, E, is the force on the charge divided by that same charge. E would be the electric field. Okay, let's go ahead and draw an example of what an electric field looks like for some of these objects. We have a positive charge on the first one. Notice I have these separated by a wall. Okay, I don't want you seeing how they interact with each other. We're going to just begin with a positive charge. So in a positive charge, it's much like the sun. You have an electric field that's emanating from the charge. Okay, and it goes out everywhere in all directions outwardly. For a negative charge, we're going to have quite the opposite. A negative charge would be like a black hole. It's going to go ahead and consume, if you will. So in the first case, with the positive charge, the electric field goes away from the charge. For a negative charge, the electric field gets absorbed by it. It goes toward it. It's attracted to it. Okay? Now, in these above pictures, let's show areas of weakness and strength. So we have that the area of strength is going to be here near the charge. So the electric field is strongest near the charge. As you get further away, it becomes weaker. And of course, you get to a certain point where it is very weak. Okay? As you go further away from the electric field strength is weaker. It has less of an ability to affect other things. With the case of the negative charge, same idea. As you get nearer the point charge, it becomes stronger. Again, if you want to think of this analogous to a black hole, obviously, the further away you're from a black hole, the less likely you're going to get sucked into it. But if you get closer and closer to the black hole, it's going to definitely suck you in. Okay, so again, if we're further away from the electric field, then it'll be weaker. Okay, and again, this is three-dimensional, so I'm talking about like this whole region right here would be weaker. This whole area right here would be stronger. Okay, and everything in between would be something to that extent. Now, what happens if we take the wall off? This is called an electric dipole. So remember that for a positive charge, the field goes away from the positive charge, and for a negative charge, it goes toward it, into it. Well, if we take the wall off, and these are close enough, they will actually affect each other. So what happens is that we have this electric field line going this way, and then this one curving. They curve because they're three-dimensional. Some of them will be weaker, some will be stronger. Notice the direction of the arrows that I'm drawing, right? So obviously, and then, some of these are bending slightly. Some of these electric fields are bending slightly. Okay. Notice how the strongest connection is going to be the one right down the middle. That's going to be your strongest interaction in this electric field. And then these aren't too bad. Okay. These are decent. As we kind of get further away from this, notice that there is still obviously some interaction going on here. This negative charge is affecting the positive charge's electric field, and it is slightly bending it, but it's not quite making the connection. And you can see these are also bending as well. You will notice, of course, that these are not affected whatsoever. Neither are these ends, right? These are not able to be affected by the electric field lines, by the opposite charges of both of these. Okay. So what you're noticing here is that they can affect each other. They will affect each other's electric field lines. It depends on the charge that they are. Okay. There will be areas of strength. There will be areas of weaknesses. And recall that these will be three-dimensional fields. Okay. Now, draw the interaction between two positive charges. We'll do that in the next example. But take a moment to consider this summary. Why do the electric field lines of an electric dipole look the way they do? Hint, consider the fact that the charges might not be the same. Let's begin here with two positive charges. So I'll have a positive and a positive. We're going to draw a few of these. And let me try this again. I want to draw something that's about the same size. All right. So recall that the positive charge gives it outward. Same thing with this one. They are close enough to go ahead and actually affect each other. So what happens is as these go out, they're going to be repelling each other. Okay? They're still going outward, but they're going to repel each other. Okay? Nothing's happening right here in the middle of all this, right? Because of the repulsion force between the two of them. So obviously we do have areas of strength, right? But there's strong repulsion going on right here. Okay, there's a strong repulsive force going on right there. So we kind of see the same thing going on with negative, for example. If I go ahead and were to draw two negative charges, we would see they would be going like this, except the arrows would be going in opposite directions. And again, notice how it's really this area there where the strength is happening. This is not this exterior part of this negative charge is not being affected by this one over here, right? It's going to be just the ones that are most close to each other. Okay, but again, we see repulsion going on. Okay, because these are like. All right, these are not electric dipoles. All right? A dipole is a configuration where you have one positive and one negative. Okay, and that's it. We do have. Let's consider another case. Let's consider the case of, let's say, a charge that's twice as big as another one. For dramatic effect, we'll pretend this is twice as big. So the electric field will be twice as powerful. And so it looks like we expected before, but it's a little bit more dramatic. So we have it going like this. I'm doing a bad job of this. So it kind of becomes a bit lopsided, right? It's a bit heavier on this side than it is on this side. Okay. It's not as symmetrical. It is a bit lopsided. but we still have the same idea going on here. Let's do a special configuration. Let's do a positive, and let's do, let's say, a negative and a negative, and they're all the same. Same size, I should say. So, of course, the positive is going to give them out, and the positive is going to make them go outward. The negative wants to accept them. But this gets tricky, right? Because the opposites will attract, but the likes will repel. So what we have going on here is this will obviously attract, and this will obviously attract. But then what's happening here is they're going to actually end up curving a bit, right? Because these are repelling from each other. Of course, if we look at areas of strengths, this will be the strongest connection between these two charges. This will be the area of strongest attraction between these two charges. We have an area of repulsion, a strong area of repulsion in this area right here. Oops. Notice how, again, there's nothing happening in between here. So when we have repulsion going on, repulsive forces, there tends to be like a bit of a pocket right here. Okay. Let's do some math. We gave you an equation earlier. Let's go ahead and do some math. So we have a positive charge. Coulomb is going to be a charge. That's going to be Q. We have newtons, which is a force. We're looking for the strength of the magnetic field. We're looking for the magnitude. Magnitude means absolute value. Okay, so don't worry about positives and negatives. You're going to just go ahead and get an answer and ignore the sign. Okay, now recall that the formula is E is equal to F over Q. The force in this case is 0.2 millinewtons. Milli is 10 to the negative 3. And then we have 3 microcoulombs, and micro is 10 to the negative 6 coulombs. If we put this in a calculator, we're going to get 66.7 Newton over coulombs. 0.2. There's E. E is the scientific notation shortcut for a lot of calculators. You might not have this one, but your scientific calculator might have a capital E. Use that to your advantage, okay? That's capital E right here. I was able to access that by pushing the second button and then E. I'm going to put negative 3. Don't forget negative is different than a minus. And then 3e to the negative 6. And that's where I got my 66.7 from. I rounded to the nearest tenth in this case. And now we have a positive charge of 15 microcoulombs. Coulomb's going to be Q. It is located in a field. This time they gave us the electric field. And they're going to be looking for the force. So recall that E is equal to F over Q. If I want to get F by itself, I would multiply both sides by Q. So that looks like 42, look at the units, newtons over coulomb, times 15 times 10 to the negative 6 coulombs. You'll notice that the coulomb is over 1. The coulombs cancel out. You're left with a newton, which is the correct unit for force. Putting this in the calculator, 15e to the negative 6. I get 6.3 e to the negative 4. Now, e to the negative 4 means 6.3 times 10 to the negative 4 newtons. Okay. What does it look like in real life? That looks like 6.3, but I want to move it over 4 spots to the left. 1, 2, 3, 4. So essentially, 6.3 times 10 to the negative 4 is the same as saying 0.00063 newtons. Okay, be comfortable with either one of these two. Summary: how might an electric field be used to exert a force on a charge?